Last time when we met, we started taking a look at section 5.1. We've done the addition of integers portion of this material and a few other things last time. And so now we're going to move into, we have a few details to finish up from last time, and then we have the subtraction stuff that this section presents. So we had left off on the properties right here of integers last time, right? This is where we left off. And we talked about the fact that pretty much all of these are the same properties we've seen before. There's nothing new here yet about integers that we didn't have, say, with whole numbers. But Theorem 5.2 actually presents new information, and this is it. For every integer a, there exists a unique integer, the opposite of a, or negative a. It's called the additive inverse, such that a plus negative a or negative a plus a add to 0. So, just to make sure everybody's thinking the same way that I mean it, what's the additive inverse of 5? Negative 5. What's the additive inverse of negative 7? 7. Okay, good. And why are those the additive inverses? Okay, part of it's because they're the opposite, but that's not really what makes it work. Because when it adds to the other number, it equals 0. That's why it's actually the additive inverses. When it's added to its additive inverse, it equals 0. I think there was something else I was going to say. Oh, why did we not have this with whole numbers? Why was this not a property of whole numbers? Say that, Ariel. Negative numbers are not whole numbers. We didn't have negative numbers before, right? Not in that number system. So that's the reason this is a new property that we didn't have. All of these properties we had, but this one's new because now we actually have negatives. What's the additive inverse of 0? 0. It's itself, okay? So just be aware, it has one. It's not very exciting, but it does have one. One more theorem before we move into subtraction, Theorem 5.3. We've encountered one of these already last time. The opposite of a is a. In other words, the additive inverse of negative a is a. Just like I asked you what's the additive inverse of negative 7, and you said 7, right? If a and b are equal, then a plus c is equal to b plus c. We've seen that happen with whole numbers as well. That's not new. But it's true for integers too. And then on C, when we have the opposite of A plus the opposite of B, that is the opposite of A plus B. The sign stays the same, and we can add the whole number part of those integers together. All right. When we talked about subtraction with whole numbers, we defined it the same way I'm about to define it now, back in terms of addition. So integer subtraction, same thing. For any integers a and b, if we have a minus b, this is the unique integer n, such that a is equal to b plus n. And again, like I said, we've seen this before, but the idea is that the reason that 5 minus 2, for example, is 3 is because 2 plus 3 equals 5. It's the number I need to add to the 2, in this case, to get back to 5. That's what subtraction is. And that's oftentimes how kids are first thinking about it. If you know all of the addition, if you know the way addition works, then you should use that knowledge to create the information about subtraction. Last theorem, before I show you the models, says the following. Subtraction is the same as adding a negative. I have a very distinct remembrance or memory from 7th grade math where my teacher said there's no such thing as subtraction. And if you said subtraction or minus in her class, it was a big, hairy deal. She always focused on the fact that it was adding the opposite, adding negatives. That was her best way that she felt to help us understand whatever concept we were working on. I don't remember what it was, but I remember that fact. No such thing as subtraction. No such thing as subtraction. Always adding negatives. Now, that's really good, but that actually lends itself to a couple of differences in how we think about our models. So let's take a look. We're going to do a subtraction model where this is 5 minus negative 3. I'm not wanting you to take the minuses and turn them into pluses because that would turn this into an addition problem and the modeling would be lost, okay? So we're not trying to use any of those theorems to simplify this. We're trying to show that it really is the same as addition. I also have another remembrance of my brother-in-law. He's actually 2 years older than me. And he had, after high school, he didn't go to college right away. He took a number of years off and then he went back. And when he went back, he started with beginning algebra, like Algebra 1 from high school, but in a college setting. And he really struggled with why in the world is the opposite of a negative positive? Why is minus negative going to turn into positive? And so this is answering that question. Why do we get to say that when I have two negatives, I just make them both positive? I mean, like, that's fine, we can do that, but why is it true? So hopefully, after we've done a few examples, you can see the why it's true part. So create a circle just like we did last time. And with this CHIPS model, again, we're going to have black dots for our positive numbers, and we're going to have red dots for our negative numbers. So if you have, make mine a little bit thicker, if you have colors with you, that's wonderful. If not, we'll all survive, but there's my two dots. So, again, just as a reminder, these are my positive values and these are my negative values. So this starts with 5 positives, okay? So I'm going to put 5 positives in, no problem. But what this literally says is to remove 3 negative chips. What's the problem with that logic right there? There aren't any negative chips to remove, right? If it told me to remove 3 positive chips, I could do that. I'd just take the 3 positive chips and take them out of my circle, right? Again, think about the kinesthetic learners, the ones who need to touch and feel. We could do that. We can take those things out, but there's nothing in there to take out. So how do I do that? Well, the answer to that question is that you add in 0 pairs. I just added in the number 0, a positive and a negative chip simultaneously, right? Imagine picking them up out of the bin and I put a positive and a negative inside my circle. But I can do that one time, so I can do it as many times as I need to. Well, I need to do it 3 times. Why? Because I've got to take out 3 negative chips. So what I just did here, let me change the color of it. These pieces that I've added right in here, they're zeros. This whole circle right now is still equal to 5. If I wanted to, using what we had done last time, we could pair these up and we could remove them from the circle. I could take these and I could take them out because they're 0, right? They cancel each other. This is still 5 in my circle. That has not changed. Just because I added them in pairs, that's why. But now that I've put everything in the circle to be able to remove the 3 negatives, I can now remove the 3 negatives. And if I remove the 3 negatives, what am I left with? I'm left with 8 positives. Ariel?
So a negative and a negative equal positive, right?
They do.
So since there's like kind of a double negative in this question, in a way you can think about it 3 plus 8.
Right. You can, and actually what we just did verified that that's appropriate to do. So we got the answer 8 just like we would have if we recognized or if we had told the child to begin with, well, negative times a negative is a positive, and they just memorized that, they would do this as 5 plus 3. But this answers the question of why it works. At least it gives one visual representation of why it works. Okay? So the key is to put into the situation 0 pairs. Now, we're going to do the same thing. We did this last time as well, but with charges. Remember, we have the charged field model, and so I put in 5 positives. And then I want to remove, that's what subtraction means, is to remove or take away. That's how we usually describe it. 3 negatives. But there are no negatives, so what would I have to do? Put in 0 pairs, so a plus and a minus. However many of them I do, I have to have that many pluses and that many minuses. And then I'm actually able to do what I just said, which is to remove the 3 negatives, which of course leaves us with, leaves us with 8 positives. Okay, everybody good with that? Okay, the number line model. We talked last time about how the number line model's the one that I'm most familiar with, at least from my childhood, and maybe some of you are as well. And it does work very nicely for drawing, or for, not drawing, but for somebody who wants to be able to move around to think about their mathematics. I'm going to draw the screen on what it looks like, because there's not really a great way to draw what I'm about to do. But then I am going to jump the desks, not really jump them, but move across the desks like I did last time so you can actually see what it looks like if you were to do it in action. So unfortunately, because of the way that this works, whoops, let me get a solid there. Because of the way that this works, we're going to start, of course, with the 0, and we're going to move 5 to the right. And then these 2 negatives, again, indicate that I'm still moving to the right, at least visually, over 3 more to 8. So I come to 5, I come over here to 8. That's all I can draw for you visually, which again doesn't really help us with thinking about, well, why did the negative still mean I'm going right 3? It doesn't do a good job. But if I do it in motion, you'll see why it works. So we're going to start here. I'm going to go forward 5 desks, right? 1, 2, 3, 4, 5. We're going to count that one as a desk, otherwise I'm going to run out, okay? The first negative means that I would be turning around. What do you think the second negative might mean? I could, or it could mean I'm walking backwards. So I can do 1, 2, 3. So either of those representations would work, whether you're turning around twice or whether you're moving backwards to represent the -3, but a child could still count it out and visualize why then I end up still moving in the positive direction. Emily?
So with the turning around, did that make it
No,
that
we're,
turn around? You still moved back 3.
yeah, so I didn't do, oops, that was supposed to be an eraser. Let's try that again. Okay, so this one was, when I actually physically did it, this was my turnaround.
Oh, okay.
And then what I did, how I was thinking about it, again, not necessarily the only way, but was thinking about then moving backward 3. But when I turn around and I move backwards, that's still me moving in a positive direction. If you don't like that and you want to describe it the way most of you were saying, which was turn around twice, that's okay too. You could do that. So either of those will still end up making us moving in the positive direction to get the +3 on the end. And that's how I described it to my brother-in-law when he was asking those questions of me, actually, was in that number line sense. The last one, patterns. So let me work with you on patterns to see this one. We talked last time about the fact that the pattern one may not be the most intuitive for some of us, but there are kids for whom it is. So if I talk about subtracting whole numbers, this works pretty well. 5 minus 2 is 3. That we would know from subtraction of whole numbers. And if I did 5 minus 1, what would I get? 4. And then 5 minus 0 would give me 5. All that's whole number subtraction. So that's all previous knowledge that a child would have already had coming in. What happens then is to notice that as you go down the right-hand side here, what's happening to the values? They're increasing by 1, right? Kind of arithmetic sequence-like. So if I then do 5 minus -1, and then I do 5 minus -2, and I get to the 5 minus -3, which is my problem, what I care about knowing, we could still increase 1 on the right-hand side. So this would be 6, 7, and I would get to 8. So from a patterning perspective, I still end up with the same result. Now, I often have students who are like, okay, that's fine, but like if I did 52 minus 37 or you start getting big numbers, that's not very practical. I'm not going to do patterns for that. And I agree with you, you're not. The reason we're using small numbers is to establish why all of those rules I gave you work. They're answering the question for the student, but why? But why is a negative times a negative a positive? Okay, so yes, at some point we get to the point where, yes, I just need to memorize the multiplication tables, right? This is with the child. But remember when we first did multiplication, we talked about the why. It's repeated addition. But I don't want to repeat addition and have to think about it that way forever. But the explanation of the why at the beginning, it's very helpful. Does that make sense to everyone? Okay. A couple last things in this section are PEMDAS, which is not necessarily as intuitive as it might sound. I know you have seen this before. Yes, ma'am, Emily?
I don't know, so I was thinking about the pattern.
Yeah.
And so it goes up, but then you get to 5 minus negative 5, and it just goes back to 0.
No, it wouldn't.
Oh, just kidding. That's
Yeah, it would keep going because we would still have the negatives. We would, so if you did 5 minus negative 5, you'd have 10.
I didn't think that was
Yeah.
wrong.
Yeah, but that's actually good to be aware of because there are children who could do this part just fine. But once the numbers match, just kind of like what you were thinking, they still revert back to thinking, well, those are the same numbers, they become 0. So recognizing that fact is a good thing, that's a common place to make mistakes. Yeah. Okay, does anybody know an acronym that they've memorized or have learned before for PEMDAS, PEMDAS? Emily?
Excuse my dear.
Oh. Yes, that's right.
Sorry.
Has anybody heard any different ones? Occasionally I have people who have. That's it? Everybody's got please excuse my dear Aunt Sally? Okay. There is one caveat to this that is highly unfortunate in memorizing the order of things, and this is it. The M and the D really don't have an order, and the A and the S really don't have an order. So if we had actually memorized this as PEDMAS, P-E-D-M-A-S, it would still be correct. Or PIM, I can't put the D and the S-A in the wrong order. I start being able to not do it. But there isn't really an order for the MD or the AS. Yes, multiplication, division comes before addition, subtraction, but there's not like multiplication has to be done before division. That's not true. So let's write these down, and then we'll talk about an example of this. So this P is for parentheses, of course. What was E for? Do you remember? Exponents. Oh yeah, and by the way, parentheses means simplifying inside of them. It doesn't mean getting rid of parentheses, it means simplifying inside. Sometimes you can do that, sometimes you can't. M and D are what? They're multiplication and division. I'm going to just write multiply and divide for short. And then A and S are addition and subtraction. Add and subtract. So you can subtract before you add. Are you okay with that? And you can divide before you multiply. The kicker is that once you get to the point where you're supposed to either multiply or divide, you simply move from left to right. Once you get to the point where you're supposed to do the addition and subtraction, you move from left to right. So let's do an example to see one. So I've got 5 minus 2 plus 6 divided by, 5 minus 2 plus 6, divided by 2 times 4. There's no parentheses, right? So I don't have to worry about the P, and there's no exponents. So I'm actually at the point where I need to decide if I'm going to multiply and divide. Do you see any of the places where you should multiply and or divide? Yeah. All the way here, right? So once I get to a point where I see multiplication division, I do it from left to right. So this is 5 minus 2 plus, what's 6 divided by 2? 3, and then I have 3 times 4. So the next step then would be that the 3 times 4 is 12. And then again, now at this point I'm left with addition and subtraction, but I move from left to right. So the first thing I would do is 5 minus 2, which would be 3, and then I do 3 plus 12, which would be 15. There are several questions, or there's a set of questions, I should say, in your book that ask you to do order of operations, but the way they ask their question is they say, what is your last step? So what is the last step that we actually did here? We did the addition of 3 plus 12. So that's what you would answer to that question if it were posed for this problem. What's my last step? 3 plus 12. Or you could say my last step was to add 12, and that'd be okay as well. But that would be how I would describe my work on that last step.